The spectrum of the modulated signal can be expressed. This is capital Phi double sideband as a function of frequency. We can express this as AC divided by 2 times capital X of F minus FC plus AC divided by 2 times capital X of F plus FC. If we draw a sketch of the spectrum, we have a copy of the spectrum of the original message signal centered at plus FC, and it would look something like this perhaps. And then we have, and it has a height of AC divided by 2, and we have a copy of the spectrum of the message signal centered at minus FC. It also has the same scale. You'll notice there is no component for the carrier. There is no carrier component. This is in contrast to the conventional AM or amplitude modulated signal, and we will see that component when we look at the AM modulating system. But there is no carrier component. That's why we call it suppressed carrier. If we draw a dotted line centered here at the carrier frequency, we can identify two sidebands. One sideband above the carrier frequency, that is the upper sideband. Here's the upper sideband. And we also have a sideband below the carrier frequency. This is obviously the lower sideband. And similarly for the negative frequencies, toward F equals 0, we have the lower sideband, and for on the higher side, away from F equals 0, the upper sideband. Taken together, this is a double sideband amplitude modulated signal. This is in contrast with what we will see in the future with a single sideband signal. Now let's look at the bandwidth of the modulated signal. This is the bandwidth of the double sideband suppressed carrier modulated AM signal. So to create this signal, we took the message signal into a mixer where it was mixed with the carrier, AC times cosine 2 pi FCT. And the result of this multiplication operation produced the double sideband signal, which would be equal to x of t times AC cosine 2 pi FCT. If we look at the spectrum of the original message signal, it might look something like this. We have a shape for the baseband spectrum that is goes from 0 out to a bandwidth of B. So again, measuring bandwidth only over the positive frequencies, we get a bandwidth equal to B. The spectrum of the modulated signal, as we just worked out, is a replica of the baseband spectrum, replicated and shifted to the carrier frequency. Again, if we measure the bandwidth over the positive frequencies again, we will measure a total width of 2B. So the bandwidth of the amplitude modulated signal is twice the bandwidth of the original message signal. Let's consider the power in the double sideband suppressed carrier AM signal. So to find the power, I'll start with the equation, the time signal equation. Phi double sideband of t is equal to x of t times AC cosine 2 pi fct. The power is found by taking the time signal and squaring it. Double sideband. I got the this is double sideband. So if we square the time signal and then take the time average, that will give us the average power. So we're going to take x of t times AC cosine 2 pi fct, and we're going to square that signal and then take the average power. And so that's going to give us x squared of t, and that's going to give us an AC squared and then a cosine squared of 2 pi fct. Then we're taking the time average of all of that, which will be x squared of t times a squared. Cosine squared, we can apply the trig identity 1/2 plus 1/2 the cosine of twice this angle, which would be 2 pi times 2fc times t. And now we're taking the time average. And if we distribute through this term, we will have two terms. We will have x squared of t times AC squared times 1/2 plus x squared of t times AC squared times 1/2 cosine 2 pi 2fc times t. And we're taking the time average of this sum of two terms, and we can find that time average by taking the time average of these two terms separately and then adding them together. So for the first term, 1/2 is a constant, AC is a constant, so AC squared is a constant, and now we have the time average of x squared of t. And then we're adding to that, for the second term, we've got a cosine at twice the carrier frequency, and it's being amplitude modulated by this this term, which is these are all positive numbers. So it is time varying, but they're all positive numbers, and so this is nothing but an amplitude modulated cosine centered at twice the original carrier frequency, and it's going to have a time average of 0. So that second term time averages to 0, and we're left with the power in the double sideband signal. This is the average power. In double sideband signal, equal to 1/2 AC squared times, this is the average power in the message signal. Okay. We will come back to this equation and compare it with the results for the other modulation systems. Okay, so we'll remember this result.